I'm going to talk about some work I've been doing in the last couple of years with my student Felix, who is up in the audience, and Loganayagam, who is somewhere also up in the audience. This is sort of concerns what we've been thinking about in the context of trying to write down an effective theory of hydrodynamics from first principles. My aim today is to give you a rather broad brush picture of where we are at with this theory, and leave details and some implications of our construction to Loganayagam, who will speak in the parallel session on Thursday. There we go. So much of what I'm going to say, some of what I'm going to say is contained in a couple of papers I wrote with these guys and some work in progress, and hopefully by the time I'm done you'll understand where all these terms in the title come from. So let me begin by asking a following question. Suppose you ask yourself, say you have quantum field theory, it's in a density matrix, it's not a pure state. How do you do Wilsonian RG in this context? Now I would say characterize the status quo as follows. We have a reasonably good phenomenological understanding, we have very good physical intuition of what's happening in the system, but I don't think we have a very good theoretical understanding of how to derive the low energy field theory when we are in these mixed states. The main crux here is the fact that when we are in a density matrix, our system, a quantum field theory, may be entangled with some other degrees of freedom which we are not keeping track of, and sort of not quite knowing what this entanglement structure is being ignorant of that is central to the discussion, as I'll point out in a moment. Now this question is not sort of just random theoretical interest from the point of view of a quantum field theorist or many body physicists, but it impacts a lot of discussions in the context of black holes and of course cosmology. So to give you a feeling, let me start with a microscopic picture where I think things are under much better control. So let's say you have a mixed state. You can always purify a mixed state. You can purify a mixed state by introducing some ancillary degrees of freedom and consider your system not just as your original Hilbert space that are given, but in some enlarged space. So you can take a pure state in some tensor product Hilbert space, and this idea is central to the Schwinger-Keldysh construction of how to compute real-time correlation functions in quantum field theories, because once you sort of have a pure state, you think of a density matrix where you evolve the ket, if you like, forward, the bra backward, and sort of piece them together in a path integral to construct the density matrix element. Of course we know that this is sort of much more interesting when we put the quantum field theory in a gravitational context, we do holography, because then these sort of the bras and the kets spaces get sort of mixed up and geometrically conjoined in the context of black holes, sort of ER equals EPR sense. Now this is sort of microscopics, but if you sort of ask what the macroscopic picture is, things are sort of different. We understand, so I've drawn here a phase diagram of where the origin represents global equilibrium, the horizontal axis represents fluctuations away from global equilibrium along some momentum or frequency, and the vertical axis represents amplitudes of fluctuations. So global equilibrium we sort of understand very well, because we can sort of basically use the techniques that we have time tested techniques of Euclidean generating functions, etc. Linear fluctuations which sort of stay at low amplitude are also well understood, basically by resorting to a Schwinger-Keldysh construction. We can compute time ordered correlators and understand how things work. There is another regime which is under much better phenomenological control. This is the fluid gravity regime or the hydrodynamic regime, as I'll explain in a moment. But there is vast space in this phase diagram which is sort of theoretical terra incognita. So we have no idea how to sort of construct from first principles a non-equilibrium dynamical quantum field theory that works in this regime. And I sort of mentioned the word entanglement moments ago, and I'll tell you what the point is. Say you were sort of set up the Schwinger-Keldysh path integral for microscopics and tried integrating out stuff. So while initially all you did was entangle the two systems, as you integrate out stuff, you induce interactions between the two copies. And this, as Feynman and Vernon sort of postulated more than 50 years ago, leads to what are called influence functionals that sort of couple the two systems. And if you don't control the influence functionals, you will run into tension with things like microscopic unitarity. So let me tell you the phenomenological theory in the regime where we are sort of at arbitrary amplitudes, but at small momentum. So this is the regime of hydrodynamics, which captures the physics of fluctuations of this density matrix, but the fluctuations are arbitrary amplitude, but they're restricted to be of low momentum. The macroscopic emergent variables in this theory, in this regime, are basically the intensive parameters that characterize your Gibbs density matrix. You might call them temperatures if you are and chemical potentials, and fluid velocity that tells you how energy and charges are exchanged across various domains of locally equilibrated stuff. And I'm going to collectively call all the hydrodynamic variables psi, and in my accounting I'm also going to allow myself the freedom to introduce external sources just so that I can monitor the response of the system as I turn on the sources. So I'll have a background metric that couples to energy and momentum, and a background gauge field if I have charges that couples to the flavor charges of the system. It's actually convenient and as you will see somewhat useful to combine the intensive parameters on this velocity into the following quantities. I'll call a vector field the thermal vector, which is basically the fluid velocity normalized by temperature, and I'll relabel the chemical potential divided by temperature in terms of a flavor gauge parameter, which I'll call lambda beta. So beta, which is basically, if you think of equilibrium, beta sort of picks out the size of the thermal circle and puts a direction to it, whereas the thermal twist tells you how flavor charged objects twist as you go around the thermal circle. So this is sort of the basic variables. So what are the axioms, if you will, of hydrodynamics? If you're a hydrodynamicist, your job is very simple. You try to monitor conserved currents, energy, momentum, charges, etc., as a functional of these hydrodynamic variables psi, and since you are in the low momentum expansion, you can sort of systematically expand these conserved currents order by order in some kind of gradient expansion. This is, if you will, a sort of a different way of doing, it's a way of doing effective field theory, but one where you sort of work directly with currents instead of effective actions. The dynamics of this theory is very simple. It's just conservation modulo potential work done by sources and anomalies if you have them in your theory. I've included them because it's sort of useful for various purposes to sort of diagnose the constraints of the hydrodynamic effective theory. So here are the equations of motion, energy conservation up to anomalies, and Joule heating, and charge conservation up to anomalies. So if this was the whole story, hydrodynamics is a very simple theory. We could just stop here, but there's a important phenomenological constraint that's usually imposed on hydrodynamic effective field theories, one which says that in addition to these conserved currents, there's a new object. There's an object which is macroscopically emergent, which is this entropy current, and it emerges because we want our hydrodynamic system to on-shell respect the second law of thermodynamics for every configuration. So usually one says that one has an entropy current, which is also a function of these fluid variables, and on shell it's required to have non-negative divergence. There's a lot of evidence for this phenomenology from various first principles, including kinetic theory, and if you like from fluid gravity, corollary of area CFT, that this is the correct macroscopic picture, but we haven't sort of derived this from any Wilsonian effective action point of view. Now, to sort of tell you what the problem is, it's the fact that there is this odd object, the entropy current. Where does it come from? So it's a current that's not a priori associated with any conserved symmetries. It's just there, emerges macroscopically, and it's required to satisfy some sign definiteness condition for its conservation. I'm going to sort of make the following assumption. It's not required, but I think, as I'll try to convince you, this is a consistent set of a nice story emerges if we make the following assumption, that there is a new symmetry in the emergent, in the low energy description, a new abelian symmetry, which I will call the KMS gauge symmetry, which couples to the entropy current, and in particular the entropy current is just the Noether current of this abelian gauge symmetry. This per se sounds really weird, but I'll give you one clue that in the context of gravity, entropy of black holes is realized as a Noether charge, as Wald and Ayer famously pointed out more than 2 decades ago. The symmetry is dynamical, and we'll see that it controls the influence functionals and make sure that they respect microscopic unitarity, or macroscopically ensure that the second law of thermodynamics is respected. So let's ask, where does this symmetry come from? And to give you an answer, I'm going to tell you a slightly different story for a second. So we had these postulates for hydrodynamics, and these postulates have existed. You can read about them, for example, in Landau-Lifshitz textbook. But let's ask, can we solve the structural aspect of hydrodynamics? Can we completely classify all constitutive relations, as a hydrodynamicist would, which are consistent with the second law? And so we undertook this task in the last year, thanks to various developments that have happened in the last 7-8 years, and we showed that we could classify all acceptable hydrodynamic transport in 8 distinct classes, one of which accounts for dissipation, and in addition there was a class of explicitly forbidden terms that you can understand by studying hydrostatic equilibrium. A technical tool that we found very useful was to formulate the entropy production statement instead of as an on-shell requirement, but as a complete off-shell statement. And to do this, I'll talk about this object we introduced called the adiabaticity equation. It basically allows you to sort of, what we did was to take linear combinations of the entropy production with equations of motion with Lagrange multipliers suitably aligned with the hydrodynamic fields beta and lambda beta, and delta here is the total amount of entropy produced in the off-shell process. For technical reasons, actually it's useful to switch from the entropy current to a free energy current, basically doing a microcanonical grand canonical ensemble switch, but the details are not important. So here's the free energy current and the free energy adiabaticity equation. So okay, so we have this structure. So what do we learn from here? So here's the answer. So we have these 8 classes, which I'll just read out to you. So we have a class, 4 classes which are alphabetically named. One of them corresponds to quantum anomalies, how they imprint themselves macroscopically in hydrodynamics. Second class is a class of constitutive relations that seem to talk to things like Berry curvatures in the extended hydrodynamic phase space. A third class corresponds to topologically conserved entropies. And a fourth class, which is in the center, is the dissipative class, which we're all familiar with, the part that says that hydrodynamics is a dissipative theory. There are 4 more, and to discuss them, it's useful to sort of split up the free energy current into a piece that's along the thermal vector and a piece that's transverse to it, and that sort of distinguishes the S subscript from the V subscript, and you can sort of either be hydrostatic, that is you're in equilibrium, or you can be actually hydrodynamic. There's actually a very interesting statement here, which is apart from this bottom class of the south pole, which is the forbidden class, which you can obtain from hydrostatic analysis, as was completely argued convincingly in this paper by Shantanu Bhattacharya, building on earlier work she had done with various people in this audience. She also argued something very interesting, that if you think about the dissipative transport, then the dissipative transport is constrained to be by the second law only at leading order. So in other words, if you think of the hydrodynamic effective theory, there are dissipative terms, and the dissipative terms only the leading irrelevant dissipative terms have some definiteness constraints. Everything else sort of follows with no constraints at all. So we said, okay, and I should point out that everything on the outside doesn't produce entropy. It's only the dissipative class that produces entropy. So in terms of the adiabaticity equation, delta vanishes for all but class D, which means that we are sort of in a sort of adiabatic limit when we are sort of talking about the 7 classes which are on the outside of the circle. So we should expect to be able to write down an effective action which captures these in a suitable sense. And how did we do? We actually did pretty badly if we tried to do this. We were able to do 2 classes, which I'll tell you in a moment, very easily, but the remaining 5 classes which were of adiabatic kind, we weren't able to write down a simple effective action. We had some partial success with anomalies, I'll mention that in a moment, with Berry transport, and various other people had tried, but there was no consistent story. So to give you a feeling for the 2 classes which I mentioned, which are the hydrostatic scalars and the hydrodynamic scalars, the answer is very simple. You just write down a Landau-Ginzburg free energy function as a functional of this hydrodynamic fields. You think of this as a sigma model which maps some space filling brane which is immersed in the fluid and maps from that to the physical fluid. And a nice consequence of this sigma model is that if you look at the diffeomorphism, the whole volume diffeomorphism and flavor invariance, you immediately with a canonical definition of entropy, you immediately recover our adiabaticity equation. We get the equation I wrote down as a off-shell Bianchi identity. To get dynamics is a bit more complicated. I won't explain it in detail, but what you need is that it's not a regular sigma model. You need a sigma model with a sort of preferred vector field that sits on the world volume, and if you vary fluctuations about this vector field, then you get the correct dynamics of current and charge conservation. But this is not very satisfying, so we sort of said let's look at the other classes, and we already had some intuition when we studied how flavor anomalies are imprinted in hydrodynamics that we should take the Schwinger-Keldysh construction of density matrices seriously. We should sort of double the number of degrees of freedom. So empirically, with various bits and pieces of evidence, we stumbled upon a single Lagrangian density which worked for the 7 non-dissipative classes, the adiabatic classes, but in the process we learned that doubling wasn't good enough because doubling didn't prevent us from forbidding terms that would be in tension with the second law of thermodynamics. So we needed to double, and we only doubled sources, as I'll explain, but in addition to doubling we also needed to put in some additional constraints through the presence of an emergent symmetry that forbidded a class of that ensured that we don't get back the class of hydrostatic forbidden terms. So the Lagrangian we wrote down had the sources, the fluid fields, their partner, what I would call the Schwinger-Keldysh partners in course, and in addition a new gauge field that ensures adiabaticity. And the Lagrangian is very, very simple. This Lagrangian has just linear couplings of the physical currents to the partner fields, and the new gauge field that we posited couples to the free energy current. The claim that this works to give you all the desired 7 classes, and it reduces it's sort of when restricted to special cases to cases that had been studied of non-dissipative effective actions in the literature. The nice thing is that it sort of does exactly what I wanted, that the free energy current is the Noether current of this KMS flavor invariance. And I'll just mention here that this linear couplings to the partner fields is highly suggestive of certain structures that are encountered, as I will mention in a few words, in linear dissipative systems and in topological sigma models. So what I'm going to do now is take the symmetry seriously and ask if we can go for the full story. Can we actually work out the full theory including dissipation? And now I'm going to tell you in the next couple of slides a story that I think holds water, but not all the details have been worked out. Till here we are pretty confident, we have sort of shown all of this works, but the rest of it is something that's work in progress. So as the vice person once said, surprises might always be there. All right, so I'm going to go back to microscopics for a second and tell you some important things in the Schwinger-Keldysh construction, or rather I'm going to interpret certain things that are sort of manifest in the Schwinger-Keldysh construction but are not thought about this way. When you double your fields or sources to sort of talk about density matrices, you introduce some intrinsic redundancy. In fact, if you sort of think about having sources for the or operators inserted in the Ket space, the right space, or the bra space, the left space, you can sort of you can realize that the Schwinger-Keldysh construction involves Kets forward and bras backward. So the natural Lorentzian structure in this space. So you can sort of pass on to a light cone basis of average and difference operators, and the time ordering relations of Schwinger-Keldysh tell you that the difference operators are in a topological sector. So there is a field redefinition symmetry, if you like, which I will interpret as a BRST symmetry, which says that these difference operators are in some suitable sense BRST exact, and this is necessary to get to ensure the Schwinger-Keldysh prescription gives the correct time ordering. So first statement is that you have doubling, and doubling also gives you a set of 2 BRST charge and its conjugate, which I'll call QSK after Schwinger-Keldysh. But there's something else. You can go look at equilibrium. In equilibrium, you have a global thermal circle And we're used to thinking about this global thermal circle because when we talk about equilibrium, we do Euclidean path integrals. So I can sort of connect the left and right Hilbert spaces by not by going in an ADS CFT sense through a EPR wormhole, but rather by just orbiting along the Euclidean thermal circle. So a half period rotation in the Euclidean thermal circle takes me from the right to the left, and this in turn allows me to define another basis of operators, which I'll call the advanced retarded basis. And in this retarded basis, I've explicitly stuck in for statistics factors. In this case, I've imagined these operators are bosons, and F beta is just the Bose-Einstein factor. Now, because operators on the left and right are related by a thermal shift, there's a non-local symmetry relating them, which basically says that the entanglement structure at finite temperature is non-local in position. But if you go to very high temperatures, this Euclidean circle, whose size is set by beta, collapses. So there's an approximate sense in which local symmetry emerges, and I will assume that what that means is another pair of BRST charges arises, which I will call the QMS BRST charge, and as you can rightly guess, this is going to be related to the KMS flavor symmetry the KMS symmetry that I mentioned to you moments ago. So with this, now I'm ready to tell you what the answer we think is. We claim that hydrodynamics is a low energy theory of spontaneously broken diffeomorphism and flavor invariance with an emergent U1 symmetry. The macroscopic variables, which are the Goldstone modes of broken diffeos and broken flavors, are precisely a vector field and a scalar field, which are the thermal vector and thermal twist. And you can sort of write down at least a theory that captures the topological sector of hydrodynamics by thinking about how probe particles of various codimensions feel the fluid. How are they buffeted by the presence of fluctuations in the fluid? And the claim is that the world volume theory is just a gauge topological sigma model incorporating 4 topological supercharges, which are these Schwinger-Keldysh supercharges and the KMS supercharges. This is sort of, in fact, the theory we think is a very close variant of the theory that was written down to study S duality in topologically twisted n equals for super Young mills more than 2 decades ago by van Witten. And of course, we are not interested in just the topological sector. We want to consider physical fluctuations, and we think we can do this by turning on sources for average fields and working out theory of space filling Brownian branes. So just to convince you this is not complete rubbish, I'll give you an example where this is just true. It's an example that dates back 4 decades and is well known in certain communities. So think of Brownian particles, which in my analog are 0 branes. So if you have a Brownian particle, you can imagine it sort of undergoing a sort of stochastic Langevin equation. So here's the equation of motion, where on the right hand side I have some stochastic noise. So XF has some autocorrelation function, which is delta function. Now this system can be given a Lagrangian interpretation if you are willing to double. It's a dissipative system. There's eta here, which says that there's friction. But this construction goes back to these folks, Martin C.G. and Rose in the 70s. But mathematicians would recognize this as something that's well known in mathematics literature as the Mattei-Quillen construction. Basically, you can sort of introduce auxiliary fields, write down an effective action, and rewrite that effective action in terms of the Schwinger-Keldysh parameters. The price you pay for having BRST symmetry is that you have these ghosts. In fact, this theory is nothing but the topological field Morse-Witten theory for supersymmetric quantum mechanics. The Brownian brane is a bit more complicated because then you have higher dimensions, and you also have to worry about the fact that dissipation in hydrodynamics is not linear, it's non-linear. So the story is consistent with everything we know, and it has a bonus. If you look at linear dissipative systems, the macroscopic manifestation of KMS symmetry is the famous Einstein-Smoluchowski's fluctuation dissipation theorem, and it's incorporated very cleanly in the Lagrangian that I told you. It's just a statement about what the ghost kinetic terms are doing in this theory. It's also supported by various experiments that you can do in ADS-CFT, but I won't have time to talk about how this works. In the last epsilon minutes that I have, or maybe minus epsilon minutes that I have, let me quickly tell you how this might be actually useful in practical purposes. To do this, I want to tell you that our classification for hydrodynamics is consistent with all the pieces of data that we've checked. But to sort of illustrate the point, I'll talk about a neutral conformal fluid in our basis up to second order in gradients. So here's a stress tensor. It has the usual ideal fluid part described by a pressure, a viscous part described by viscosity, and there are 5 transport coefficients which I've written in a basis that's somewhat unfamiliar to most of you because I've adapted them to a basis that's common, that's naturally suggested by our classification. So in this basis, there are 3 terms that are hydrostatic. These 3 terms, the gray ones. These 2 terms are dissipative. This term belongs to the Berry curvature form. It's sort of suggested by the fact that there's a parity odd vorticity term here, and here is a term that's hydrodynamic. And if you sort of look at the transport coefficients of this theory, you find some interesting accidental relations in Einstein gravity. For example, the second order dissipative coefficient actually vanishes. The claim which I want to alert you to is that if you forget about viscosity for a moment, you can write down a very simple effective action basically by doing answer analysis that reproduces everything including at first and second, at 0th and second order, which is just this effective action that I've written down here. This is basically a form of our class L Lagrangian where I have turned on sources, so there's curvatures here and so on and so forth. It will be extremely interesting to derive this from gravitational dynamics in first principles. There are some ideas that go back few years ago by Nickel and Son, and some people have tried, but all that succeeded is get the partition function or the ideal fluid part. The fact that these transport coefficients, the second order transport coefficient vanishes in Einstein gravity suggests to me that there's a new principle at play, a principle that I would like to call an optimal dissipation conjecture, that holographic fluids not only minimize their value of shear viscosity as we know, but also ensure that the amount of entropy produced is minimized in any fluid flow. It will be interesting to see if this is related to various other bounds, as I'm going to say in a moment, on chaos, equilibration, and scrambling rates in holographic systems. Anyway, so I'm wrapping up. So we have the claim is that we have a topological field theory with an emergent gauge symmetry that captures the low energy dynamics of near equilibrium hydrodynamic systems, and our construction was aided in large part by the fact that we were able to completely give a solution to the structural aspects of hydrodynamics, a story that could have been done quite a few decades ago, but we have, thanks to ADS-CFT, a lot of data to check this against, and so that was useful. There are a lot of open questions, but since I'm out of time, I wanted to close by making the following remark. On Friday, we are going to celebrate a great theoretical milestone of Einstein's discovery of general relativity. But there are 2 other things that happened in that year, which I think are quite seminal. One was Schwarzschild's discovery of black holes, and the other was Noether's understanding of how symmetries lead to conservation laws. And I just want to point out that if you just follow your nose and take this principle seriously, you get quite far even today. Thanks.
Hi, Mukund. I just wanted to point out that the connection between Brownian motion and Morse theory was actually first pointed out by Shumit Das, Gautam Mandal, and myself 25 years ago.
Yes. I'm aware. I have not put in all the references, but yes.
Hi, Mukund. Positivity of production of entropy appears to be one of the restrictions on consistent hydrodynamics, but there may be others.
Yes.
For instance, the hydrodynamics of superfluids appears to be constrained by the so-called Onsager relations.
Yes.
I was wondering whether there's some interplay between other constraints in your classification.
Okay. So I have something to say about Onsager relations. So we have this class of terms which you are very familiar with, these class B terms. They explicitly violate Onsager relations, because Onsager relations assume some kind of time reversal symmetry, and I don't think that Onsager relations are generically true. It may be that if you impose them, you get further constraints on the class of allowed terms, but in our analysis you would explicitly forbid class B terms. And just to illustrate that, the fact that we see the class B term, which was coupling of shear to vorticity vanishing in n equals 4 plasma, is just an accident. I should point out that things that people know of, like Hall viscosity, are explicitly of this form. So if you believe in parity odd systems, which you can realize experimentally, then I don't think Onsager relations are just true.
So is it your conjecture that there are no further restrictions other than positivity for entropy production on the
in the low energy theory? I think this is true. Of course, we haven't sort of done a classification for everything except for relativistic fluids. It's an interesting question to ask if you have other Goldstone modes in your problem, whether you have other constraints that crop in. We don't know.
Other questions? Well, if there are no other...
So I have a very naive question. So you have this topological field theory, right? So topological field theory doesn't have a stress tensor, or the stress tensor is 0?
Yeah.
What's the physical?
Yeah, so I think the topological part of the theory, you have to couple it to external sources that generate the physical stress tensor. So that's the part I said, that you have to deform the topological theory to give you the physical answer that you want. But I'm saying that the symmetries allow you to constrain the topological sector very efficiently, and then you add in the sources for the physical operators, which are the average operators of the Schwinger-Keldysh construction, and they would give you the physical stress tensor of interest.
The zero stress tensor is the difference operator. So
That's
the
right.
difference between the two stress tensors.
That's correct.
So in view of the time, let's thank the speaker again. We'll start 11. The next session will start at 11:05.